Welcome to my algebra class. We are on chapter 4, section 8. We're going to be doing chart problems that involve uniform motion, which means motion that does not change over the course of a traveling object. We're going to be using the formula rate times time equals distance. And we'll have two objects that are moving, and we'll need to know how to represent their rate, their time, and their distance. And then we set up the equations. And the equations are one of three types. Either the uniform motion, the objects are going in the same direction, like this little boy walking to school in the morning, and then his little dog walks to school in the afternoon to meet the little boy when he gets out of school. They both travel the same distance, so we set D equals distance 1 equals distance 2. If we have a round trip, for example, the boat travels to a location and then comes back from that location, that's a round trip. So the distance going to that place is equal to the distance coming back. So that again, the two distances are equal. Opposite directions, an example of that would be two planes leaving an airport, one going east and one going west. So the total distance that they travel, you have to add those together. So the distance the first plane travels plus the distance the second plane travels in opposite directions equals the total distance. Be sure and copy your vocabulary in your notebook. This would be a good time to do it. When you're done, you need your paper and your book turned to page 170. Paper's headed, skip a line. Titles page 170, problems 1 to 15. On page 170, the directions for the first 4 problems is a copy. Complete the solutions for the oral exercises 1 to 4. So turning back to page 169, we're going to start by making the chart first. And labeling the columns rate, time, distance, and the objects reading the problem for number 2. At 8 a.m. the Smiths left a campground driving at 48 miles per hour. At 8:20 a.m. the Garcias left the same campground and followed the same route, traveling at 60 miles per hour. At what time did they overtake the Smiths? So we drew a picture of what's happening. They're both leaving the campground. They're both traveling the same distance. So distance 1 is going to equal to distance 2. Labeling the rows, we have the Smiths moving and the Garcias. They say that the Smiths left the campground traveling at 48 miles per hour. So we put 48 here. And the Garcias left the same time, followed the same route, and they're driving 60 miles per hour, so that's their rate. The time, at what time did they overtake the Smiths? We don't know, so we'll put T here. T is the total time for the Smiths traveling. The time for the Garcia, since the Smiths left at 8 and the Garcias left at 8:20, the time for the Garcias is 20 minutes less than the time for the Smiths. Now remember, the rate was given in terms of miles per hour. So you have to take that 20 minutes and convert it into a part of an hour. So 20 divided by 60, that's 1/3 of an hour. So they left, their total time is the Smiths minus 1/3 of an hour. So the distance for the Smiths is 48t, 48 times t, rate times time. The Garcias, use your distributive property, it would be 60t minus 60 times 1/3 is 20. Now we said the two distances are equal to each other, so 48t has to equal 60t minus 20. solving, we get the variable on one side. Since 48t is by itself, we want to bring the 60t over. That gives us negative 12t equals negative 20. Dividing by negative 12, we get t equals positive 5/3, or 1 2/3 hours. And the question was, when will the Garcias overtake the Smiths in 1 2/3 hours? So if we started at 8 a.m. and add 1 2/3 hours, 2/3 of an hour is 40 minutes. So it would be 9:40 a.m. is when they overtake them. So please be careful on the times on these problems. Since most of the rates are given in terms of hours, if there's minutes involved, you have to convert those minutes into parts of an hour. Problem number 4, make the chart for it. Columns again are labeled rate, time, distance. And in number 4, it says Jenny had driven for 2 hours at a constant speed. When road repairs forced her to reduce her speed by 10 miles per hour for the remaining 1 hour of her 152-mile trip. Find her original speed. So we can break this up into uniform motion by making 2 different times for her, or 2 different speeds. Her original speed and slower speed. And it says she had driven for 2 hours at a constant speed, so we know how long she drove at her original speed. It was 2. And when the road repairs came up, it reduced her speed by 10 miles per hour for the remaining 1 hour of her trip. So 1 hour she went at the slower speed. So how do we represent her rate? Well, it said it reduced her original speed by 10 miles. So if this is x, her slower speed is x minus 10. Multiplying out rate times time, we get 2x for the distance of the original speed. And distributed property 1 times x minus 10 is just x minus 10. Now how do we set this up? She's going a total of 152. So you have your first distance plus your second distance equals the total distance. So this is an addition problem. So we take 2x plus x minus 10, and it has to equal her 152-mile trip. Collecting like terms, we get 3x minus 10 equals 152. Add 10. We get 3x equals 162. Divide by 3, and x equals 54 is her miles per hour, is her original speed. And they wanted to know her original speed, so that's it. Problem number 6, set up the chart. Label, rate, time, distance. Number 6 says at 7 a.m. Joe started jogging at 6 miles per hour. At 7:10, Ken starts off after him. How fast must Ken run in order to overtake him at 7:30 a.m.? So we have Joe and we have Ken. And Joe jogs at a rate of 6 miles per hour. Remember the rate's in terms of an hour. And 7:10, Ken starts off after him. How fast must he travel? So we don't know his rate. The total time, if Ken's going to overtake him at 7:30, the total time that Joe has been jogging is 7 a.m. to 7:30. That's half an hour. So put a half. Ken started out at 7:10, and he's going to catch him at 7:30. So that's 20 minutes. 20 minutes is 20 over 60. That's 1/3 of an hour. So Joe's distance is 1/2 times 6, or 3. And Ken's distance is 1/3 x. Now this is going in the same direction Joe's running and Ken's following. So distance 1 equals distance 2. So 3 equals 1/3 x. Get rid of the 1/3, multiply both sides by 3, reciprocal. So we get 9 equals x. And that's Ken's rate, so it's 9 miles per hour is how fast he's going to have to travel. Number 8, draw the chart. Label it rate, time, distance. Number 8, it takes a plane 40 minutes longer to fly from Boston to Los Angeles at 525 miles per hour than it does to return at 600 miles per hour. So this is a round trip. It's going from Boston to Los Angeles and then from Los Angeles back. So the two distances are equal to each other. So the two objects moving is the plane going to its destination and the plane return. And going to Los Angeles, he was traveling 525 miles per hour, and returning returning at 600 miles per hour. Says it took the plane 40 minutes longer to fly from Boston to Los Angeles. So if x equals the time, coming back it was shorter, going to it was longer, so it was 40 minutes longer, so that'd be x plus 2/3. 40 minutes is 2/3 of an hour. So the distance of the plane going to Los Angeles was, use your distributed property, 525x plus 2/3 of 525. That's 175. 2 times 175 is 350. And 600 times x is 600x. And the two times are equal. Two distances are equal to 525 plus 350. That should be 525x. Plus 350 has to equal 600x. Getting the variable on one side, since 600 is by itself, we want to move the 525 over there. So we get 350 equals 75x. Divide both sides by 75. And 350 divided by 75, I can't think right at the moment, so I'm going to get my calculator out. It comes out four and 2/3. And that's the time it took the plane coming back, 4 2/3 hours. And the question is, how far apart are the cities? Well, you can take, this is the distance right here from returning back from Los Angeles. So you could just take that one and plug in the 4 2/3. So 600 times 4 2/3. That's 600 times 14/3. Cancel. So the distance apart, 14 times 200, is 2,800 miles. Problem number 10. Make the chart. Label the columns, rate, time, distance. And then problem number 10. It took Cindy 2 hours to bike from Abbott to Benson at a constant speed. So she's going from Abbott to Benson. The return trip, Benson to Abbott, took only 1.5 hours because she increased her speed by 6 kilometers per hour. How far apart are Abbott and Benson? So we have Cindy going to Abbott and Cindy coming back. It took her 2 hours to bike to Benson, and coming back it only took her 1.5 hours. And it said she increased her speed by 6 kilometers. So if X represents her original speed, coming back, X plus 6 would be her new speed. So the distance would be 2X going to Abbott. Coming back, use your distributive property, it would be 1.5X plus 6 times 1.5 would be 9. Two distances are equal to each other, so set up the equation that way. 2x equals 1.5x plus 9. The 2x is by itself, so subtract 1.5x from both sides. So you get 0.5x equals 9. Divide by 0.5. So x equals 18. And that's how fast she was going originally. That's her speed. So if I want to find the distance, I need to take the time and times it by her speed. So 2 times 18. The distance from Abbott to Benson is 36 miles. Or kilometers. I think it was kilometers. We're going to stop there. I think originally I had only gone to 10. So if you go back to the top and just change your assignment from 1 to 10. That concludes the evens. Be sure and check your answers in the back of the book. Get help from me. Take your time with the problems, not too much time, however, and make sure you're doing them correctly. Get help as needed.